Hello, my name's Clive Tong and I'm a software developer here at Redgate Software. I spend most of my days working on .NET Reflector, which is a decompilation tool which will take .NET assemblies and give you a C# or VB view of the contents. Today's presentation is going to try and cover the changes that are coming along in the C# 5 release that has just come out from Microsoft. What I'm going to try and cover is a brief history of C# so far, going through the versions that we've seen and the themes behind them. We'll then look at the theme for the latest release of C# and the .NET 4.5 framework, and then we'll have a little look at C# 5 itself, look at the breaking changes it has brought about, look at some of the new features, and have a look at Async, so the asynchronous programming side of it, which seems to have been very popular. So the versions of the .NET framework that we've seen so far. Well, in my opinion, .NET 1 was essentially a better Java that came along about 10 years ago in 2002. Microsoft introduced value types and non-virtual methods in order to get good performance, and had a focus on a more sort of component-orientated language, including things like events and properties, including good interaction with managed code and COM. And over the years, it's come through 5 subsequent releases with different themes behind those releases. So C# 2 came along with generics in about 2005, which was a big improvement, allowing more efficient collection implementation, or that was the way we first saw it. So rather than having collections just over the object type, you could actually specify types for the elements within the collections, and therefore avoid all the casting when you fetch the values out of them. This was the last major change to the virtual machine itself. So the introduction of generics required changes in the IAL instructions and the runtime representations of things. This was in contrast to the Java way of doing things, where the actual generic implementation was stripped out or elided from the compiled code in order that they didn't have to change the virtual machine. C# 3 came along in about 2007, which introduced a general querying language that got built into C#, and also introduced some amazing GUI technologies like WPF and Silverlight that we have today. It also introduced anonymous types and lambda expressions, but the key point with this was that these were all implemented by the compiler via a sort of code generation with no support from the underlying CLR. So C# 2 was the last time the CLR really changed. The later versions of the language are built on top of it, but have used the code generation technology inside the compiler to avoid having to add special hooks or IAL instructions back into the virtual machine. C# 4 introduced dynamic language support, so they added a dynamic type that deferred method lookup until runtime, so it sidestepped the usual strong type checking of the C# compiler. Basically, that meant that if you interacted with COM components, you didn't have to put .item all over the place, but could put more natural-looking property and method calls, and the compiler would work out at runtime whether those were applicable or not. Recently, we've come across C# 5, whose main theme seems to be asynchrony. The world itself seems now to be full of applications that need to talk to applications, but bandwidth and other concerns like latency mean that you might be waiting for your reply for a very long time. So we need some way in the language to make it easy to write code that doesn't hog resources, but can react to events that might take a while before they come back to us. So the theme for C# 5 and the 4.5 release of the framework is basically fixing some long-standing language issues. We'll see one's a common source of bugs, the second is a way of optimizing a common pattern. But the big feature is really a change to a language and framework to support responsive applications, and we'll talk more about what that means later. First, we'll go through the breaking changes. So there are 3 breaking changes that C# 5 has brought to the language. The first one is the classic puzzler of having a closure that references a variable that's being looped across. So in this small piece of code here, you can see that we do a for each across an array containing 5 elements. And each time we make a closure that references the loop variable. If we then add it to the collection and run across them at some later point, we find that in earlier versions of a language, the variable value that's closed over, well, we're actually closing over the location of the variable rather than its value at the time that the closure is made. So we get the value 5 from all of the calls. In C# 5, this has been fixed so that we actually end up closing over a location, but it's not the location of the actual variable that's being changed on each loop iteration. So we get the answer, the more natural answer that people expect when they see it. Though we do get a nice compiler warning that warns us that we're accessing the for each variable in the closure, and this may have different behavior when we compile with different versions of the compiler. The second issue was the evaluation order of named arguments. In C#, the method arguments are normally evaluated in left to right order, but in earlier implementations of named arguments, this wasn't the case. So here we make two closures. The first one prints 1 and returns 1. The second one prints 2 and returns 2. And we call them expecting the leftmost one, which returns the value 2, to be called first. When you run this in earlier versions of a language, you actually find they're called in a different order. So the compiler has generated code which uses the named argument first, evaluating that, and then using the second argument. So we no longer see this left to right pattern. This has been fixed in C#5 to generate things in the expected left to right order. There's also been some changes to overload resolution. So there are some very complicated side scenarios where the resolution didn't work as people expected, that involved named arguments calling methods that contains a params parameter, and cases where there's a choice between a func object and a func of some other type. I'll let you go to the MSDN website to get the details of that. There are two new features basically in the language that are interesting to us. The first one's the implementation of iProperty notify change, which is a common pattern that seems to be, well, a common interface that seems to be more and more important these days, and the introduction of async. So data binding seems to be everywhere. People are using MVVM and such patterns to have objects and have GUIs subscribed to those objects in such a way that the GUI gets notified when values inside the object changed, in order to implement data binding. And what we'd like is a really concise implementation of this. So here we have a typical class that has a single field in it, and whenever the field is changed, we need to raise this property changed event to tell anybody who's listening in and data binding to us that things have changed. So the classical implementation of it from .NET 2 days is something like the code we see here. One trick I should point out is that assigning a null delegate into the property means that you can make this code slightly more concise than having to check to see whether property changed is null before you call it down in the last line of the setter code. When Link came along, people started coming up with clever ways to enable you to refactor the code. In the first implementation, we had a problem in that we had a property and we needed a string containing the name of that property that we could raise using the notify change mechanism. People used expression trees in order to allow them to pass in a lambda expression here that contains the property itself. By defining the call property changed event in the right way to take an expression tree, an expression as its argument, you can actually get the compiler to give you the code of the lambda expression rather than something that actually represents the compiled lambda expression. This allows you then to destructure it and find your way to the actual property. So now we have a nice bit of code where we're actually referring to the property in two places. This means that if we do any refactoring, changing public int property to public int property 2, the lambda expression that we use in call property change will automatically be updated as well, meaning that we keep the correspondence between the thing that we raise and the string that we pass in the property changed event and the actual name of the property itself. C#5 goes further with this. So what we really like is to get rid of any of these tricks, any of this hackery to do with lambda expressions. And this is what C#5 does with this new caller member name attribute. So what we can do now is make a call to this call property changed function, passing in no arguments at all. And the trick is that this function can take an optional argument, which we default here to be the empty string, that's annotated with this caller member name attribute. This tells the compiler to actually replace or call as the first argument with the name of the method in which the call is made. So the code we saw before is now completely simplified to this. At runtime, name will be assigned property and will get passed through the change callback mechanism without us having to do any hackery. In addition to caller member name, they've also added caller line number and caller file path as attributes that you can use on arguments to optional arguments to a member. When you use this, you'll see that in this simple function I call here, the member name is main, the line number is 13, and the caller file path is actually the name of the source file that was compiled when this method was made up. But of course, the main feature that's got all the attention is async. So it's interesting to look and try and think what sort of world we're in now and why we need a big change to the language that async represents. So I think there are two things. First, we're in a world that encourages responsive programming. So we have tablet computers, and in a tablet computer, when you do something like a drag interaction with the GUI, you need quick and fairly instant feedback in order to make the whole application feel responsive. It's very frustrating if you're dragging an item and it glitches on the screen. It doesn't feel that it's really stuck to your finger. So the async feature that they've added to the language tries to make it easier for programmers to express computations which require background work to happen. In the past, they've done things like introduce the background worker and thread pools, where you, the programmer, were responsible for spawning off this work, passing it somewhere else and then keeping an eye on it. But it's very hard to program in such models. The essence of web and cloud and mobile computing is really asynchronous programming. Getting data from remote sources adds unexpected delays owing to things like latency. And we don't want our client to be sat there waiting to get the response and seeming to hang to the user. So the canonical example people use for this is a simple Windows Forms application with a button on it that's going to cause some code to execute. This code is going to call out to the file system, so when we press the button, we'll add a button-click handler that's basically going to make a data buffer, open a file stream, and do a read from the file stream, and then write out some information it got back. The trouble is, this doesn't look like a potentially blocking application, but the read call on the file stream could take a very long time to execute. Or it might take a long time if we're running this on the GUI thread, which might cause our GUI to glitch in a way that makes it frustrating for a user to use. It's interesting to see when we enter the button handler as we're about to call the read method, what the state of the call stack is. So we set a breakpoint. We're at the breakpoint of the foo method inside the button click, as we can see here. When we look further down the stack, we notice that we're actually running inside the message loop. So most GUI application frameworks have a special thread on which you're expected to do all your interaction with the GUI. They do this because they want to avoid complicated synchronization code and locking. So it would be very bad news indeed if we were, for example, updating a list box and concurrently on a different thread, someone was making changes to that list box. So GUI libraries generally put a constraint on that all interaction with the GUI must happen on a single thread. And that's the problem with this example. The thread itself is handling messages by using this message loop queuing concept, but while our button click handler is running, we aren't able to process any more events on the GUI thread. So we're not able, for example, to repaint the windows. So it seems to a user as if the GUI dies. So this is a little diagram of what really happens. The Windows system sends events, which it puts into a queue. So we say we have two events in the queue, the first one being the button click, and the second one being a paint request, telling the system that we need to redraw a part of the GUI because it's been destroyed during the clicking process. The message loop code we saw basically pulls a single message from the queue and dispatches it. So it dispatches it into our button click handler. When the button click handler finishes its work, which potentially takes quite a while because we were doing that file read and we're not quite sure how long that's going to take, it returns back into the code that's running the message loop, which can then pull the second message out of the queue and dispatch it so it can then cause the repaint of the GUI. We'd really like our button click to return very quickly, choosing instead to run these time-consuming processes on maybe a different thread. So what we'd really like to do is to somehow break down the method at this point, the point at which we're calling the read method. so that we can return back to the message loop and continue processing GUI events. But we would like the read somehow to do the extra work, so the console.write line, when it's finished getting the information together, so when it's actually finished the actual read operation on the file system. And there are several ways we could think of doing this. So one way frameworks like Node.js do it is to use a lambda expression. So a lambda expression allows us to capture local variables at the time we're making the call to the read. So the idea is we can pass in this lambda expression. The read to call can happen on some other thread, allowing our button click to return and therefore start processing more messages, with the understanding that when the read to finishes, the actual read to function itself calls the lambda expression with the results. We're going to call this lambda expression, or the code inside it, the console.write line in this case, the continuation. Now there's going to be a few subtleties about this. We want to make sure that continuation runs on the right thread, because, for example, the continuation could itself manipulate windows. So we need to make sure we're back on that special thread that's allowed to interact with the GUI when the lambda expression runs. Just to make it clear how this lambda expression fixes things, let's go through the previous example again. So again, we have the two messages, the first one being the button click and the second one being the paint. The idea is that the button click handler is run, it gets to the read to message, which basically schedules the read operation maybe on a thread pool or using the operating system and getting a callback from the operating system when that finishes. We don't really care. All it's done is stashed away the lambda expression for later execution when the data is available. That's allowed us to jump back into the message loop, which can then pull in the paint message, which can then be dispatched. At some later point, the read to finishes on the background thread, and that can take care of firing us a message onto this thread again that lets us execute the rest of the lambda expression now that the data is available. So we've now managed to get things into a state where we can return fairly quickly and process Windows messages, keeping the GUI looking very, very responsive. But of course, we've introduced one or two problems in the meantime. So we've introduced reentrancy. Before, if you click the button, you couldn't click the button again because it was disabled until the click handler had finished. Now the click handler only runs a little bit, then returns, allowing us to potentially click the button multiple times. So obviously we would need, in this case, if we were restructuring our code in this way, to disable the button after it's been clicked and only re-enable it when the click handler is finished. So that would be extra code we'd have to add into that continuation. But maybe that's something we should be doing anyway. The whole problem with the previous example is that we had to write the lambda expression ourselves, and it makes the code look very complicated very quickly. So what we'd really like is compiler support for this, and this is what the async feature gives us. So we're going to show you what help the compiler demands from our classes in order to allow it to do this transformation of breaking a method into multiple sections that get executed independently of each other. So what I've done is I've changed the use of a file stream to a class called myFileStream, and I've changed the foo.read method to be the foo.read async method. So this is a naming convention that Microsoft are using when they add asynchronous methods that you don't have to wait for the results of to the framework. So we've changed the class, we've changed the method. What we really would like to do is just to put a marker in our code to tell the compiler at which points it can break the flow of the code up. And C#5 introduces the await keyword to allow us to do this. So by putting this await keyword in this place, we're telling the system that we expect the first part up to the await to start executing in one block. But then we're happy for the rest of the computation, the stuff that follows the await, to happen after the computation, the read async, is finished. The compiler is going to take our existing method, work out the places, code gen the relevant blocks of code, and hook into our code in such a way that it knows when to continue the computation. So what do we really need to implement in this case? Oh, I should have also mentioned, in order to know that the method is special and hence needs this special code generation, you have to mark it with this async modifier. So you're only allowed to use these await expressions in a context in which the whole method itself has been marked as async. So this is the myFileStream class. When we call the read async, we basically return an instance of this myFileStream waiter. We have to return an object that represents the state of the computation, and we'll see in a minute that that object has to obey a certain pattern in order for the compiler to be able to hook into it in the code that it generates. The myFileStream waiter supports this public method called getAwaiter. So the pattern here works much like enumerators in C#2, where you have a getEnumerator method. We don't have an interface that describes that the class can handle enumeration. The compiler will simply look for a public, accessible method called getEnumerator in order to know that it can do the for each form across instances of the class. So a waiter is the same idea, a pattern that basically returns another object which is going to have certain methods guaranteed on it which allow the compiler to continue a computation later. A common implementation that you'll see in the framework is that the getAwaiter method will return this, but in this case we don't do this. In this case we return this status object. So this status object has to support two properties. It has to support a isCompleted Boolean thing, which will tell the compiler whether the operation is finished or not. So obviously it's a bit time consuming for the compiler to generate, inefficient for the compiler to have to go into a state where it's waiting for something to finish before it can continue the computation. So there's a sort of shortcutting mechanism where the compiler first checks to see if the operation is already completed before it goes into blocks of code that have to set up the whole waiting behavior. So in this case I just return false, but obviously in the real case it would depend on the results of the method. And the second pattern it looks for is a getResult public method, which actually returns the final value. So my read operation actually has a final value of type int, so I need to have a getResult method that returns an integer. So here, to get the compiler to type check it, I've just hardwired the value 10. The key point is that this object supports this iNotifyCompletion interface, and this has an onCompleted method which gets past a continuation action. So the idea here is that our implementation will do whatever it needs to do. By the time it finishes, the compiler will have called onCompleted to pass us this action that we need then to call to tell it that it can get on with the second part of the continuation from the method that we were awaiting on. So the pattern has these three things. It has the getAwaiter on the original class, isCompleted, getResult, and a non-completed method. From just those things, the compiler can transform an async method with some number of awaits inside it into code that has the behavior that we want. Okay, so we've skipped over a couple of things. What happens if we need to return something? So our original button click handler basically had a void return type. Say we need to return the data read, the integer value of the number of bytes that were read. How do we actually return that from button click, knowing that the actual data read value won't be available till later, until the read sync or async operation has actually finished? We can't keep the void, we need to change the type to be something else. It turns out in .NET 4, Microsoft added the task parallel library to the framework. So this was a very cool library that allowed us to both encapsulate the notion of a future and the notion of a bit of code that will complete at some later point. So here we have an example showing what you can do with tasks. So first of all, we can define a task which returns an integer whose only job is to run this lambda expression. This lambda expression here. So the idea is a task encapsulates the execution of this bit of code. Tasks allow us to take blocks of continuation and paste them together. So here we can generate a second task, and this task here basically just takes a value from the first task and continues and writes it out when the task finishes. So when we start the outside task, it will run the first bit of the task, which prints started, done, and returns 20, and then we'll continue with the task that was added as a continue with to the first task. The tasks also give us properties to tell whether they've completed and their status. So if we look and see what this bit of code does, we'll see false and waiting for activations for the is completed and the status properties before we call task.start. After we've started it, it will still return false and waiting for activation until the actual task starts executing on the thread pool. We can then see the write lines that are returned by the actual execution of the task. And finally, we'll get a task is completed set to true and the status value of ran to completion. So this is just the kind of thing we need in the async case. We need something that encapsulates a value that will become available at a later stage. So this is what they've leveraged in order to implement async. So if you want to be able to return a value from a method, an asynchronous method with an await in it, it must return one of these task types, which is a generic type that allows you to actually specify the value that's held by the task and which will become available at a later stage. Obviously, our continuation can throw an exception, and it turns out the task itself is also nicely geared to handle this. So the task itself, in this case where we generate a task and throw an exception, has a property is completed on it, which returns true, and a status that says that the task is faulted, giving us a way to get hold of the exception to a later stage. Now we're slightly sidestepping the issue of what happens if an exception is thrown in the case of the button click handler, which had a void return method, in the sense that there would be no task value that represents the value that's eventually returned by it. So it's hard for us to know if anyone's waiting for the value. So there's a little line in the C# spec that specifies that in the case of void returning methods, exceptions that get thrown will actually be passed across to the synchronization context on which the await happened and raised on that context. So if, for example, you're running a Windows Forms application and you have an await, like our button click handler, which throws an exception, the exception itself will actually be raised back on the main Windows thread, giving you a chance to hook in using the normal mechanisms for handling exceptions. This brings up the question, though, of context. So in .NET 2, they introduced the notion of a synchronization context and an execution context, which capture some of the state of a thread. A synchronization context represents a grouping of threads and is used in cases like a WinForms application as a way of telling you what the main thread of the WinForms application is, so that you can always get your messages, get your Lambda expressions marshaled back onto that thread before they execute. So in this example, we see that synchronization context.current will give us the current synchronization context. We then queue some work onto the thread pool, which does some stuff, but then uses context.post in order to pass a Lambda expression back to that synchronization context, back to that main Windows thread for the execution of its body. Execution context is another concept you'll come across. An execution context is basically the security information for a thread. And this is automatically flowed by all sorts of methods in the framework. So for example, when you call a method on the thread pool, your security context of your calling that's live at the time you make the call is automatically flowed across to the thread pool thread, instantiated on that thread pool thread before you actually call it. This means that, for example, if you're running under a particular Windows identity and you make a thread pool call, the code that you pass across onto the thread pool and which executes there will be running in the same security context. It'll turn out that synchronization context is a very important one. So in the bit of code we wrote, we didn't actually take any care in marshalling the result of the button click, of our read async, back onto the synchronization context of Windows Forms. So we didn't actually execute that continuation in the right place. We didn't actually execute it on the single GUI interacting thread. So if that continuation had contained any code that did anything with controls on the window, we'd have got a cross-thread exception. So this example just shows what happens if we're running this bit of code on the thread pool we put a breakpoint, we see that the console.writeLine is actually running on the thread pool. But when we get to the write line that's nested inside the lambda expression that was passed into context.post, we see that we're actually back onto the main message loop handling Windows Forms thread. Right, so we need to have a quick look and see what code the compiler's code generated. Async and await's very nice in that everything is done by the compiler and a little bit of support code in the runtime library. So there are no changes again to the CLR in order to get this all implemented. So what we're going to do is we're going to use Reflector to look at the code that's generated. Now recently we've done some work in Reflector to actually understand C#5 or the .NET 4.5 framework as we label it here. So if I take that button click method that we've been using to flow through this discussion, we can see that Reflector understands about the code that's code gen by the compiler, and it's been able to generate C# code that looks very much like the code I started out with. So we can see the await, we can see the async. If I turn down the framework level, we get a much better view of the code that's really been generated by the compiler. So the first thing that we notice is that our button one click method actually now consists of something that makes an instance of a structure type, this button one underscore click greater than d double underscore 0, into which various parameters of the function of the method have been placed before we go into some other code. So the compiler has basically replaced our method with something that takes an instance of something else and makes some other calls on it. So we need to understand what code has been generated inside this method. So when we look at this structure type it's generated, we can see that it contains some fields that are named very much like the local variables that we had in our original button click handler. So this is the sort of pattern you'll have seen if you've looked at how lambda expressions are compiled by the C# compiler. What it does is essentially lift out local variables to make them fields inside a new class that it generates in order to allow them to persist and be shared by multiple activations. So we can see some fields corresponding to data and data read. We can see the original arguments to the button click handler, which were the sender and the event args, are also added to this structure type as fields. We can see that this pointer that was active at the time the button one click handler was called is stored away as well, because obviously we're now going to be making calls on methods that now reside within this new class. So we need a way to get back to this pointer that was active at the time that the button one click was called in the first place. The other interesting method we see on this button one click d double underscore 0 structure is this move next method. Now if you've looked at the decompilation of enumerables before, you'll have seen move next. Move next basically sets up what's called a state machine in computer science terms. Every time we call move next, we basically end up transitioning that state machine by one state. In our case, in our button one click method, we basically had two states within the method. We had the code that was called before we went into the await, and we have the code that we want to call after we return from the await. And this is going to be used. It's going to be modelled by using a state machine, and it's going to be the move next method that transitions between these states in order to get the code to execute as we expect it. I should also mention that there are some extra auxiliary variables that the compiler introduces. In particular, it introduces this greater than, less than, t double underscore stack, which is used in the context where you have multiple await expressions. So I could, for example, do int x equals await foo plus await bar. And in that case, each of the awaits would correspond to another state in the state machine, and the values that they return would be pushed onto this temporary stack variable and used later by the compiler to actually generate the final result of the computation. The actual state of the machine itself is reflected by this state field. And if we go back, we'll see that it starts with the -1 value. So the move next is the important bit. So here we look at how Reflector has reconstructed the C# code for this method. So what happens is the state machine mechanism is set up, and then the very first time the button one click is called, we call move next with the state set to -1. This will cause us to go into this bit of code which basically is the piece of code from the original method that initializes the local variables. The compiler has used the pattern on our... we then go into the bit of code that calls the read async and uses the getAwaiter method, which we added to that class, as our means of interacting with the compiler. It's got the awaiter, so it checks to see whether the operation is already completed. If it's already completed, we can just go away and call the getResult method straight away. We don't need to worry about temporarily returning in order to come back later. So we've completed, we get the result out of the awaiter, and then we do the console.writeLine call that we saw in the continuation. If we hadn't completed, we basically set things up so that the state variable will be 0, and we go into this await on completed. This is the bit of code in the framework that's going to go to our object and register the action continuation delegate into our class that we, by the protocol, agree to call later when we have finished. So we can now return from the button click handler. At some later point, we'll finish the read operation and we'll call the continuation that was passed to us earlier. This will cause us to come back into the moveNext method with the state as 0, which causes us to enter that break statement, which causes us to go through the same code we saw before. So we'll pull the result out and we'll execute the continuation. If any exceptions happen during this whole process, there's a try-catch block around the entire moveNext method, which catches the exception and then pushes it into the result. So most methods would really be returning a result, a task. So this would actually be setting things into the exception property of the task so that people could look at it later and pull it out and see what went wrong. In the case of success, we call the setResult method, which just basically notifies people that the task is now finished. So what we've seen is that the multiple parts of code in our original method have been code generated into blocks that use this structure instance to maintain the state of the local variables, and which use this state field in order to record how far we got through the thing. So at this point we also set the state to -2 so that debuggers and other tools can tell that the asynchronous method has actually finished its execution and we don't expect it to be called again. Now, when we were talking about implementing the getAwaiter pattern ourselves, we glossed over the fact that we didn't do anything to handle the synchronization context. We didn't have any code in there that tried to transition us back to the original synchronization context that was in operation at the time we did the first half of the method. So in practice, it turns out that you don't really want to be implementing such things yourself, but we're wanting to use an implementation that Microsoft provides. So what they've done is they've taken the task type that's part of this task parallel library that's been around since the .NET 2 days, and they've extended it so that it understands awaiters. So here in Reflector we can see the task type, and we can see its getAwaiter method, which returns one of these task awaiters. The task awaiter itself looks much like the awaiter we wrote before. So it supports the iNotifyCompletion interface, it has a getResult on it, and it has a getIsCompleted. But both of these can hook into the existing code that exists within a task to deal with its status property to tell whether things have completed or not. When the onCompleting is called, we can see it calls this onCompleted internal method, and it passes in 2 extra parameters, one to say whether we should continue on the captured continuation, and one to say whether we should flow the execution context. The point here is that by default, the task, when you go into an await on it, will be capturing the synchronization context as well as the execution context, and will take care on re-establishing that before it calls the onCompleted. So if you do an await on a task, when the thing you're awaiting finishes, the result of the await will be provided to you back in the original synchronization context, which is something you usually want and something you don't want to be writing yourself because you can easily get it wrong. So here we can see the bit of internal code that sets the continuation for the await. So we can see it grabbing the synchronization context and capturing the execution context too. When the task resumes later, around the call of the callback function, the continuation that was passed in, we'll re-establish the execution context and the synchronization context as well. Task itself is very useful, so they've not only added the awaiter support into the task type, but they've added ways for you to customize the execution. So you can actually decide yourself whether you actually want to capture the synchronization context or not. So they provide this configure awaitable method on the task, into which you can pass the value false to say, actually, you don't want to do this synchronization context handling. You don't want to guarantee that things are executed back on the synchronization context. You know that the code that follows can execute on any thread, and you don't want to go to the overhead of doing context capture and re-establishment before you continue. Tasks also support cancellation, so they're a very useful thing to have. So they have a notion of you being able to pass in a cancellation token and signal this token at a later stage in order to tell the code running within the task that it should stop execution now. So where do we find async in the framework? Well, virtually everywhere. So for Windows 8, Microsoft decided that they want things to be very responsive. So I believe that anything that takes longer, potentially longer than 50 milliseconds, all methods that take longer than 50 milliseconds now have an asynchronous version of them. So if you look on a class like FileStream, you'll see that they've added a read async, which does the same sort of functionality as the normal read, but returns a task of int, and which runs asynchronously, and you can await it. They've also added a write async and a flush async. It's quite instructive to look at FileStream because you can see other patterns that we used in the past for trying to do asynchronous computation. So FileStream itself supports the begin and end invoke pattern that Microsoft introduced years ago in order to try and make it possible for people to do asynchronous programming, but it turned out to be not useful at all because it was just very hard to do. If you look in classes like XML Reader 2, you'll find read async methods corresponding to most of the standard non-asynchronous methods as well. So what did async give us? Well, it gave us a really easy way to write code in a linear fashion, but which pauses without locking a resource. So it's an easy way to write responsive applications without having to use the old-fashioned patterns that we used in the past, the begin invoke pattern, the end invoke pattern, and the use of things like background workers, which were very hard to deal with and just convoluted your code, making it very hard to tell what was going to run now and what was going to run later, and who was responsible for continuing the computation at a later stage. And that's it. So basically we've looked through some of the code in Reflector to try and see some of the stuff that the compiler code generates for us in order to implement this pattern. So I encourage you to go away and look at things like the task type to try and understand how it makes it easier for you to do asynchronous programming in the future.